So this related rates problem says that water flows through a large funnel that is in the shape of an inverted cone. It enters the funnel at 0.5 meters cubed per minute. The funnel is 4 meters tall and has a radius at the top of 3 meters. Okay, so it's much wider than it is tall. When the water is 1.5 meters deep, the depth of the water is increasing at 5 centimeters. Okay, that's an important point here because they changed units on us per minute. How fast is the water exiting the funnel here? Okay, so let's take a look at what do we know. Okay, and maybe let's zoom in a little bit on this. Well, we know that we're talking about a funnel that's 4 meters tall, and then the radius here is 3 meters. Okay, now that's just for the funnel though. We're interested in the volume of water that's inside there, and so the water is going to go up here. There's going to be its radius. Here's its height. It's a little bit hard to see there, so let's just take a look at the important information that we're getting out of that. This is going to be 3. This distance here is going to be 4, at least this whole distance here, because the water is going to fill it up to some sort of point here. This will be the radius of the water. This will be the height. And then what we know is that there's going to be some similarity between the large triangle and the small triangle, and we're probably going to have to utilize that. Like at some point here, I'm probably going to have to make use of the fact that 3 over 4, that to that, is going to equal radius to height. Because that will be true of the water, okay, in that funnel. No matter what height it's at, that ratio will hold as long as it's in this funnel. Okay, now what else do we know? Well, we know that the volume in to the funnel is going to be 0.5 meters cubed per minute. Okay, that's how fast it's entering in. We know that we're interested in the moment when the height is 1.5 meters. And we know that the height is changing. Okay, sorry, what does it say here? It says when the depth of the water, when the water is 1.5 meters deep and the depth of the water is increasing at 0.5 meters. Okay, so we know that the height is changing. Now I have to convert that 5 centimeters probably to meters here. That's probably the easiest way to make this consistent. So this is interesting here. In most cases, most of the time we do problems like this, we don't know what dH by dt is. That's what we're looking for. But in this case we do. And the reason we know that is because what we want out of this problem is how fast the water is exiting the funnel. In other words, there's something not quite right here. When we do the analysis here, it should be the case that we're getting a situation here where the water going in isn't elevating it the way it should. Okay, so we're going to see something different here, which is going to indicate that there's water exiting here. So let's jump into this. Here we go. So volume is 1/3 pi r squared height. Okay, this is for a cone here. Okay, now I have information about height. I really don't have much information about r squared, so I've got to get rid of r. So I'm going to use this ratio. I knew this ratio was important for something. R is going to be 3h over 4. So I can make that substitution down here and make this 1/3 pi 3 over 4h squared h. And so volume here, when I square that, what is that? It's going to be 9 over 3. It's going to be 3 pi 16 and then h cubed. So here we go. Here's volume as a function of height. Okay, so now let's jump in and take the derivative. dV by dt is going to equal 3 pi over 16 3h squared dH by dt. I'm taking the derivative implicitly with respect to time. Now I'm going to plug in what I know, but the change in volume here is going to be affected by a couple of things. What's going to happen here is we're going to get the volume in minus the volume out. Okay? Or you could think of it as, well, maybe we should think of it as plus the volume out, because if we do that, then this will end up being negative, and that will actually make sense because it represents how the volume is decreasing. Okay, so this is going to be, and I'll simplify this, 9 pi over 16 h squared dH by dt. Now we'll start to plug in the things that we know. Okay, we know that dVi by dt, it's the volume's going in by 0.5. I don't know how quickly it's leaving. We'll figure that out in a second. Okay, I know this is going to be 9 pi over 16. The height we said was 1.5 meters. That's going to be squared. And I know that dH by dt in this case was 0.05 meters per minute. Now, I got a bunch of things here in terms of decimals. I'm just going to leave it like that and we'll evaluate this. So this will be 9 pi divided by 16 times 1.5 squared times 0.05. And then I'm going to subtract that 0.5 from over here to isolate the dVO by dt. Minus the 0.5, and here we go. The rate at which the water is exiting is negative 0.3, actually it rounds to 30, okay, meters cubed per minute. That's how fast the water is exiting here. So pouring water in, water's leaving here. The height isn't quite doing what we expect it to, but that's because there's volume leaving the funnel.